Okay. So before I start, are there any questions about the logistics that you guys heard about for the project, the last couple of lectures? Is there something that you'd like to ask me before we go ahead? Something about the material that we've covered, something about the homework? Do you folks have any questions, or should I just get into the material? Okay, all right. So we were talking about translating ER diagrams to the relational model, so a collection of relations. So we had a little bit left in that we didn't manage to cover in the previous lecture, so I thought I'll start with that and then we'll move to the next topic. Okay, so we were at this point where we were discussing how to translate subclassing relationships to sort of or subclasses into relational models, right? So into relations or tables. So once again, subclasses are something you're probably familiar with by now. We talked about 3 different approaches to do this. The first approach is the ER approach, which is basically create a relation corresponding to each subclass, record all the pertinent attributes in each subclass or the relation corresponding to each subclass, along with the key for the root class, right? So because you need to identify these entities, the root class has the key corresponding to these entities, so you can use that to refer to these entities in future classes or in the subclasses, right? So here you had these 3 subclasses, or the root class, which is movies, animation, and murder mystery. So you would create 3 separate relations, right? So, and here, if you notice, title and year are underlined, and therefore that's your key. So you're going to refer to title and year in each of the relations that correspond to the subclasses. Okay, so that was the ER approach. The object-oriented approach basically said that each object can only belong in a single table. If you remember the ER one, an object can belong in multiple tables. So for instance, an animation mystery would belong both in the mystery relation as well as the animation relation. Right, so you would find you would have to look at multiple relations to find information about a specific movie. The object-oriented approach is very clear in the sense that it tries to isolate information about objects into one relation. So you have, in this case, sort of 4 different categories. Either a movie is neither an animation or a murder mystery, an animation but not murder mystery, and so on. The other 2 combinations, and for each of them you have a relation. Okay? So, and in each of these relations you list all of the pertinent attributes, right? All of the attributes that apply to that relation. For instance, for the relations corresponding to murder mysteries, you would list the weapon in addition to title and year, for instance. Okay. All right. So the last approach was the null value approach. So basically this approach says list all of the attributes that apply in all of the subclasses. So that's your entire universe of attributes. And then all of the information is present just in that one relation. And if you remember, we talked about this issue about the fact that you are losing the information about which movies are murder mysteries and which movies are animation movies, and therefore you need to add attributes corresponding to murder mystery and animation. So if you notice, these 2 attributes here were added in order to clarify whether a movie is a murder mystery or not and is an animation or not. Okay? So this was a null value approach. Everything clear so far? Yep. Voices is still another relation. So voices is not part of the subclass hierarchy, so it will still persist. Yes. Okay. So once again, there are 3 approaches: the ER approach, the object-oriented approach, and the null-oriented approach. Here's another example. So here you have Beers, which is the parent class, and ales, which is a subclass. So for the ER style, you will have one relation corresponding to beers and one corresponding to ales. In the beers relation, you have the name and the manufacturer. In the ales relation, you have the name because that's your key from beers, as well as the color, right? Because that's the other attribute corresponding to ales. The object-oriented style would have two types of beers. One is beers not ales and ales, right? And for the beers not ales case, you don't have a color attribute. For the ales case, you do have a color attribute. The last is the null value case, where you have all of the information in one relation. You have name, manufacturer, and color, these three attributes, as well as the is ale attribute, which basically indicates whether something is an ale or not. And in this case, I have chosen to signify that a beer is not an ale by using the value null. I might instead choose to use the value 0. And here I've chosen to use the value 1 for is ale. But essentially, the information is the same. Null values would probably be preferred because they are more compactly represented than, for instance, a 0. Okay? All right, so now let's talk about some queries. Okay, so let's say I wanted to find the colors of ales made by some company, let's say Triptych. So this is a manufacturer. So how would I do this? Are you guys hearing some feedback, or is it just me? Okay, if it gets unbearable or noticeable, let me know. Okay, so I'm hearing some weird sound, but I'm not sure. Yeah, there is some sound, right? Okay, it's not in my head. Okay. Let me try to move it and see if it gets better. It's unusually sensitive, or maybe it's not this. Maybe it's this. Okay. Okay. Let's hope this fixes it. It's not fixing it. It's just too sensitive. All right. So, so the first query was find the colors of ales made by some company, for instance, Triptych. The second one was find all names of all beers made by Triptych. And so before we got into that, we were talking about what would impact performance. The first thing that impacts performance is if there's more data to look at, that is bad, right? So the more stuff you need to look at, that leads to lower performance. The more tables that you need to look at, the lower the performance. Again, this is similar to more data, right? And the way we are looking at the information also impacts performance. Again, this is at a very, very high level. We'll get into details of what I mean by each of these things and how to quantify the performance of executing various queries later on. But at a very high level, the way you're looking at the tables also matters. So for instance, if you're just simply looking through the tables once, that is probably cheaper than trying to correlate information across tables. That's probably cheaper than trying to sort the information in the tables, and so on. Okay, so some of these ideas you're probably familiar with because you've taken a basic algorithms class, so you know that sorting is probably more expensive than looking through a list once, right? So n log n versus order n, for instance. Okay? So there are lots of things that can impact the performance of how a query gets executed on a database. But even without getting into those details, we can talk about which query would work faster or which approach would be faster for each of these two queries. So do you guys have any guesses for query 1? Let's say I want to find the colors of ales made by some company. So what would which approach would be preferable? Using those 3 rules, right? So I have more data, I have to look at the worse the performance. More tables, I need to look at the worse the performance. And the worse the type of looking, the worse the performance, right? The more expensive the operation I need to do, the worse the performance. Okay, so any hunches on which approach would be better for this? I don't remember if we talked about this last time. Pretend like we didn't. Yes?
The approach, because we know that we have to
Which approach? Sorry. Oh, object-oriented? Okay.
So because we have to particularly find ALs, so
Mm-hmm.
just go to that table.
Okay, so that's correct. So the approach that she suggested was we need to focus on ALs, and I'm only interested in ALs, therefore it makes sense to only look at the ALs relation. But at the same time, I need to look at the manufacturer information. Thankfully, the manufacturer information is also present in this ALs relation if I'm using the object-oriented approach. All of the information about ALs is present in that relation. So the object-oriented approach is actually a great approach for this particular query, right? And we'll talk about null value-oriented approach and the ER approach in a second. Any hunches on which one would be better for query 2? Yep.
The ER approach?
The ER approach, and why is that?
Because all of the information that you need is stored in the Beers relation.
Mm-hmm. So yes, that's right. So the ER approach would basically, so the key thing to identify here is that I'm looking for information about all beers. So that should give you a hint that perhaps the object-oriented approach isn't a great option. Maybe the null value or the ER approach is probably a better option because I'm looking at information about all beers. And in this case, I'm only interested in the names of beers made by a certain manufacturer, right? So given that I'm only interested in names of beers made by a certain manufacturer, just this relation suffices. The relation corresponding to beers in the ER model suffices, right? So, or the ER approach suffices, okay? So diving into maybe a bit more detail for query 1, like we discussed, ER versus object-oriented versus null, the object-oriented approach is better. This is because all you need to look at is the relation corresponding to beers that are ales, right? The ER approach, on the other hand, you'll need to look at multiple relations. You'll need to look at both the ales relation as well as a beers relation. And why is that? Well, you need to look at the color attribute is something that you would get from the ales relation. The manufacturer information is something that you would get from the beers relation, right? So you need to figure out the manufacturer, which is triptych, and then look for the colors of ales, right? So you need both the manufacturer information and the color information, and therefore you need to look at two relations. So the ER approach is not as good as the object-oriented approach. The null value approach is also potentially bad. This is because there's more stuff to look at. There's more stuff that you don't care about. For instance, you don't really care about the names of the beers, right? All that you care about are the colors of the beers, and there may be a lot of non-ales present in the beers relation, right? In the null value approach, right? So in the null value approach, there may be lots of non-ales, and because of that, I'll be looking at a lot of data that's not helpful to my query. Is that clear? Okay. All right, so the null value approach, there's more stuff that doesn't help my query. The ER approach has two tables to look at as opposed to one single table. The object-oriented approach, you just need to look at one table. That table contains all of the information that's pertinent to my query. There's not that much redundant extraneous information, so I'm good. So the object-oriented approach is the best in this case. Between ER and null valued approach, it's not actually clear which one would be better, okay? Possibly the null valued approach might be better, but it certainly depends on the implementation of the database. It's a priori with this level of information, I can't tell whether the ER approach or the null value approach is actually going to be better. Okay, so the only thing that I can say is that the object-oriented approach is going to be better than the other two. Any questions? Okay. So for the second query, as we discussed, the ER approach was the best because we simply needed to look at this one relation which contains information about all beers, and their manufacturers, right? So that's the relation to look at in the ER case. Why is the object-oriented approach bad? Well, because you need to look at multiple tables. You need to look at both the ales table and the not ales table, right? Because you need to find the names of all beers. It's not just the ales, but you need to look at the non-ales as well. And because of that, the object-oriented approach, you definitely end up having to look at multiple tables. For the null value approach, another downside is that you need to look at the extra color data, right? So it certainly has all of the information in one relation, but there's some extra data that you don't want to look at, like the colors, because that's not relevant for your query, right? Your query doesn't talk about colors. It's just talking about the names of the beers made by a certain manufacturer, right? So you don't need the color information, right? So the null approach, in this case, again, may need to look at a lot more data than is actually helpful for the query. Between object-oriented and the null approach, again, this is not clear. This depends on what data you have and how you're actually executing these queries. But probably in this case, the null-valued approach would work better, because the object-oriented approach is essentially going to be looking at the same amount of information as the null-valued approach, but the null-valued approach has it all in one relation. Okay, any other questions about this? Yes?
So with the null-value approach, I understand that there's more data to look at. How does that make things slower? Couldn't you just ignore the data that you don't need to look at?
Right, so good. So the question is, in the null-valued approach, don't you, given that the data is laid out in a certain fashion, don't you know the starting and ending points for the attributes that you care about? So can you not skip to those points directly, right? So as it turns out, if your data is in fact, even both if your data is loaded in memory or if it is on disk, random seeking to a certain point on your disk is actually more expensive than sequentially scanning. Okay, so jumping ahead actually costs you a lot more than reading sequentially. So often you may find that you may end up taking the same amount of time if you chose to skip as opposed to read. So that's one issue, which is it is dependent on the disk characteristics of how it's actually laid out. The second reason is that you often read entire tuples at a time into memory. You may read an entire page of tuples, which may be hundreds of tuples long. If you have other attributes that you don't care about, that's wasted space, right? You're anyway reading it into memory and processing it. Again, the details will become clear when we get into how we process queries, but hopefully at least you get a sense that it's unavoidable to a certain extent. You can try to avoid it, but the disk characteristics doesn't help you here. And secondly, the way databases process these queries is to load up bunches of tuples at a time without caring about what those tuples contain. So you can't really skip ahead. I mean, you can skip ahead once it's loaded, but the hard part is actually moving it into memory rather than processing it. The processing is the cheap part. Okay? Any other questions? Okay. Cool. So, oops. All right. So so at a high level, the object-oriented approach is good for queries where you're looking for a specific type of entity, and that's one of the relations that you're creating in the object-oriented approach. So the query like, find me the color of ales made by Triptych, you just need to look at the ales relation and you're good. The ER approach is good for queries like, find all the beers made by a certain manufacturer. So in this case, you just look at the beers relation. Using null saves space unless there are lots of attributes that are null. Okay, so if you have lots of attributes that are null, then this may actually hurt you, right? So if you have a lot of redundant attributes that you don't really use in most of the cases, then while the null approach does save space in a lot of cases because you don't have to create two relations, you can combine it all into one relation. If there are lots of attributes that are usually null, this is problematic. Okay, so the null approach usually lies somewhere between the object-oriented approach and the ER approach in most cases. But often for a given query, either the object-oriented approach or the ER approach ends up being better than the other two. Okay? All right, so yeah, again, other high-level comparisons in answering a query, we would like to have all of the necessary attributes in one place, in one table. The null approach has an advantage here. Between the ER approach and the object-oriented approach, it's a mixed verdict. This is because the ER approach and the object-oriented approach use two different criteria to split up the information. Okay, so the object-oriented approach is splitting it up in terms of objects. ER approach is splitting it up in terms of subclasses. Right? The second thing that we talked about earlier is that we prefer to not use too many relations, and for this the null method is the best because it's just one relation followed by ER, because the ER approach just has one relation for each subclass, and then the object-oriented approach. So the example that we saw, the object-oriented approach often had the same number of classes as the ER case, but as the number of classes increases, the object-oriented approach ends up having a lot more than the ER. Okay, and so this is something that there was a question on Piazza about. So if you have n, I think let's talk about the formulae again. So if you have one root entity set and n children entity sets, or n sort of descendant entity sets, how many relations can you have in the worst case, right? So in the null valued case, it's just one. You know that it's always going to be one. In the ER case, you would have one corresponding to each of the subclasses and one corresponding to the root class, so you have n plus 1. Correct? Is that clear? Okay. And the object-oriented approach, in the worst case, what you can have essentially is basically all possible combinations of the descendant subclasses, right? So you have, and this is an exercise for you. Basically, the worst case behavior happens when you have subclasses that look like this. There are other cases where the worst case behavior will happen, but the one example of where the worst case behavior happens is when the subclasses are all children of the parent class, and essentially what you have is basically you either select each one or don't select it, and so you have two options for each of these subclasses, and therefore you have 2 to the n. Okay, so there's that many subclasses in the object-oriented case, right? While in the ER case, this grows linearly as a function of n. In this case, it grows exponentially as a function of n, right? So you often prefer the ER approach if the number of subclasses is large. Okay? Any questions about this? Any questions about any of this material, because I'm switching over to another topic? Okay, all right. So that's that about translating ER models to the relational model. Okay, that's fine. Okay, so now we are going to be talking about, so we talked about how to translate how to come up with a design for a database, how to translate that into relations. We talked about those two aspects. The next question is, how do you actually query these relations? How do you query the database using the kinds of queries that we discussed when we were comparing the object-oriented versus the ER approach, right? So what are the kinds of, how do I express these queries, and how does the database answer these queries, right? So the next question is, how do we perform data manipulation? So in querying the database, we need to be able to specify what we want from the database, right? So let's say you have two relations, UIUC employee, which has SSN, name, address, and salary, and some IRS or tax information. So you have the SSN, the year of filed return, and the amount paid in taxes. Okay, and let's say I want to find all the employees who have a salary of 100,000 and yet have paid more than 50,000 in taxes. Right, so this, if I did not have a way of querying the database, the way I would do this right now is figure out how these things are represented on in my file system, for instance, and then write a program that will help me answer this query, right? So I will write a program in Python or C++ or Java that will try to suck in each of these tuples from these two relations and try to figure out how to answer this query, right? In this particular case, I want to find all of the employees who have a salary of 100,000 and yet have paid greater than 50,000 in taxes, right? So one approach is can you guys think of various approaches you would use to answer this query if you were to implement this in C++ or Java or Python? So let's say both of these relations are just stored as is in some file system, right? So these are just text files, let's say. How would you answer this query? What would your program look like? Many ways of doing this. Yeah?
Would you maybe have like a conditional and get values or get elements of the data that meet these requirements?
How would you do that? So let's say you were writing a program from scratch. So how would you do that?
Well, I guess like if you're reading the data, let's say it's like a loop.
Yep.
You examine each element, and maybe you say if element has a salary greater than 100,000,
Yep.
taxes greater than 50,000, you get that, you save that element.
Correct. So what he's saying is one way of answering this question, this question or query, right? Which is, let's say maybe I loop through all of the UIUC employees. So I go through and consider each of these UIUC employees, and then probe the other relation. Go through the entire set of tuples in the other relation corresponding to their salary or the amount they've paid, and then try to correlate the SSNs, right? So I want to figure out the employees whose salary is equal to 100,000, or I don't know what this query asks. Maybe it's equal to rather than greater than. So let's say it is equal to 100,000, and the amount that they paid in taxes is greater than 50,000. So I need to, let's say, for instance, loop through the first relation, consider every tuple in that relation, and then for each of those tuples, I will go through the second relation one by one, right? And then try to find the records corresponding to the same SSN, check if the amount paid in taxes is greater than 50,000. If so, I can output that tuple, right? Output that combination, right? So that is one way of executing this, right? So you do what is called as a nested loop, right? So you would basically loop through the first one, loop through the second one. Another way of executing this could be, for instance, to sort the first relation, right? Sort it on SSN, sort the second relation on SSN, and do something like a merge between the two to figure out which ones correlate with each other, right? The third approach may be to use a hash table, right? So have you guys heard of a hash table? You've heard of a hash table, right? So you use a hash table where you hash based on SSN. If a record corresponding to UIUC employee and IRS both end up in the same hash bucket, then you can check if they actually belong to the same person or not. If so, you can identify that person as a potential output candidate for this query. Right? These are three separate ways you could go about executing this. And a priori, there's no way where I can tell that one of these ways is going to be better than the other. Right? What is certain is that in each of these three ways, I'll have to write a lot of code. Right? It's a lot of processing. It's a lot of code. It's fairly painful to write this code, fairly painful to figure out which of these options is going to do well, fairly painful to optimize. Okay, so that in some sense is a motivation why we have database query languages and why we resort to the database to actually execute these types of queries. So like I said, you can certainly implement this in C++ or Java or Python or whatever, but in general this is a bad idea. The first reason, or the reason that we already considered, is that you need a lot of hand optimization. You need to hand tune these programs. You don't really know whether approach 1 is going to be better than approach 2. So how do you actually make those decisions up front? So there's a lot of painstaking hand optimization. Okay? The second reason is that if your query changes slightly, you may need to rewrite your entire code, right? So if I wanted to find the employees who have a salary of 200,000 and yet have paid more than 50,000 in taxes this year, then maybe I have to rewrite this, or I have to find out where to modify the program in order to be able to accommodate that, right? And even if I want to change this a little bit, if I wanted to not just find the employee names, but I also wanted to find their SSNs, then again I have to go and change this code, right? So it's not entirely easy to sort of deal with this problem. You have to keep writing code as you have more and more requirements that come in, and overall maintaining these pieces of code as you get more and more questions is simply not feasible. Okay, in the long run, this is going to lead to a lot of issues in terms of code maintenance, in terms of optimization, and in general, a lot of frustration for the developers. Okay, so this is, I don't know, today it's being really fussy. Maybe if I hold it? Okay. I don't know what to suggest. Let me try it again. Okay. All right. So the approach that we're going to be using are database query languages, or what are called high-level query languages. And these high-level query languages specify at a high level what you want from your data, and the database will actually figure out how to optimize and return the results for your query, right? So the goal is of these programming of these query languages is to be able to express queries like this in a succinct manner. You specify what you want at a high level. You don't specify how it's done. That is the job of the database. The database will figure out how to execute it. You simply tell me something that actually looks like this, something that looks like find all employees who have salary, blah, 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 right? This doesn't tell me how to execute the program. It doesn't tell me how to execute the query, but this is telling me at a high level what I want as a result of my query. If you say something like this to the database can actually figure out how to execute it. Okay, so that's the high level goal of developing these query languages. Okay, so these so-called high level query languages. They're also called high level or declarative because you are declaring what you want. You don't specify exactly how to do it. You are declaring how you want. You specify at a high level what you want. The database is actually doing all of the work for you. You don't need to figure out how to execute these queries. Okay? So this is in some sense the most arguably one of the most important concepts that you will take away from this course, which is the concept of declarativity. Okay, so being able to specify something at a high level and not worrying about how it is actually implemented. The database will figure that out for you. There's a clean separation of needs. I have needs to access the data. I have needs to sort of query it in various ways, but I won't tell you how to actually go ahead and execute that query. That is the job of the database. Okay, so these high-level query languages, which allow you to access the data in a database, they are succinct. You specify what you want at a high level, and they are optimizable. Okay, for this space of queries, the database can actually go ahead and optimize it in a fairly efficient way. It can give you execution methods that are very well tuned for this space of queries. Okay, notice that if your space of queries were everything that you can write in your Java program then there's no way I can optimize that, right? So the optimizer for a Java program is essentially the compiler. That doesn't do a very good job of figuring out whether you should be using sorting or a hash table or blah, 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 right? It doesn't help you make these choices because it is it's too expressive. Java, for instance, or Python for that matter, is too expressive, therefore it is not easy to optimize. Database query languages are more constrained, and therefore that makes it easy to optimize. Okay? So let's continue talking about this. So the two main characteristics in high-level query languages is that there's a restricted space of operations, which makes it easy to optimize, and you express how you want it, rather what you want, rather than how you want it to be found or how you want it to be executed. The thing is, this notion of declarativity is actually not special to the database scenario. Can you guys think of other examples where declarative behavior is common? You specify at a high level what you want, and the system will figure out how to execute it for you. Any examples? Yep.
Like ordering at a restaurant?
Ordering at a restaurant? That's a very abstract example, but it works. Yep. Like a hash table? True, right? So you insert, you look up. A lot of the data structures that you covered in your algorithms and data structures class probably fall into this bucket, right? The stack, for instance. Or a linked list, or you don't really, I know you probably also figured out how to implement these things, but the API for these things is still declarative. You say, oh, push it in, pop it. You don't worry about how it's actually implemented, right? Other things that you probably studied were graph algorithms, right? So if you had an API or a language over graphs which said, find me the shortest path from this guy to this guy, you don't worry about how it's implemented. You have that API call that will allow you to access that information. Another declarative behavior use case that we use fairly regularly beyond the restaurant example, which is great, is a web search engine, right? So again, you say, I'm looking for things that match this and this and this. You don't really say, oh, go and look up all of the web pages corresponding to this keyword, then take that, sort it, do this, and then take that, sort it, do that, right? So you don't specify exactly how it's executed. You specify what you want. I'm looking for web pages that have this and this and this, and the system will figure out how to do it for you, right? So this declarative behavior is common, but in some sense, the database landscape or the database community has adopted that as a guiding principle in building these database systems. Okay, so the declarative query language that we are going to be covering in the class is SQL, which is a structured query language. SQL is internally represented within data, even though the syntax and the language constructs in SQL vary from implementation to implementation, and there's a lot of sort of new features that keep getting added to SQL every day. Internally, all of these SQL queries are represented and manipulated using an algebra, which is called the relational algebra. Okay, so that's going to be the focus of today's lecture. This relational algebra is not a user-facing language, right? Unlike SQL, structured query language, unlike SQL, relational algebra is not a user-facing language. This is an internal language that allows database engines, so database processors, to figure out how to best execute database queries. So now, so yes, it's not a user-facing language. Instead, it's kind of a theoretical language. There are no database implementations that actually have relational algebra as a user-facing functionality. It's all internal. But at the same time, relational algebra is extremely crucial in understanding or interpreting these SQL statements or commands, and also is really crucial when it comes to query optimization, because internally all of these queries are represented in the form of relational algebra expressions. Okay, so what is relational algebra? So relational algebra specifies a set of operations that can be performed on relations to give new relations. Okay, so you can think of it as if you have relations R1, R2, blah, 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 Rn, and then you have this operator here, which is a relational operator. This spits out another relation R. Okay, so it takes in a bunch of relations and then spits out another relation. Okay, so that's essentially what a relational algebra defines. It defines a set of operations such that you can manipulate these relations to get new relations. So broadly speaking, what is an algebra? So you may have taken a linear algebra class. So this is probably familiar to you. An algebra is a mathematical system which consists of operators and operands. Operands are the items that you actually manipulate. So these are variables or values. And these are things that you can manipulate and from which new things can be constructed. Operators are symbols that denote manipulation operations or procedures that construct new values from given values. So you take existing things, you transform them in some way to get new things. Okay, so you have operators that operate on things, operands that get operated on. So like I said, linear algebra is a great example of an algebra. In the linear algebra case, the operands may be matrices, the operators may be matrix operations like transpose, multiplication, addition, subtraction. Arithmetic algebra is also something that you've definitely seen in school. Here the operands are numbers, the operators are the standard operators of plus, minus, and so on. Okay. So relational algebra is an algebra where the operands are relations or variables that represent relations, and the operators are sort of operations or things that we would like to do with relations in a database. So ways you want to transform relations or ways you want to query these relations. So the algebra essentially boils down to a query language for relations. This is an internal or a theoretical query language as opposed to a user-facing query language, but still this will give us a sense for how even SQL looks like. Okay, so so at a high level, this is going to be our outline for the rest of the content for this this lecture and the next one. So the operators take in relations as input, provide new relation as output. There are 5 basic relational algebra operators. There are the basic set operations, which consist of union and difference. Intersection and complement are treated as derived operators, not the basic ones. There's a selection operation, the projection operation, and the Cartesian product operation. So selection operation is a sigma, projection operation is pi, and the Cartesian product is an x. Okay? And when our relations have different attribute names, we may want to use a renaming operation. So this is not a basic operation, but it's also very, very useful in manipulating relations. So this is row. Okay, so this is the renaming operation. And then you have derived operations. So there's the other set operations like intersection and complement, and joins. Okay, so joins at a high level allow you to correlate information across multiple tables. So there are 3 flavors of joins that we'll cover later on. Okay, so let's start talking about the basic relational algebra operators. So the basic set operators are union and difference. Okay, so these are binary operators, and they operate on 2 relations at a time. So the way to think about these operators is that essentially a relation, like I said earlier, is a set of tuples, is a collection of tuples. So you can do pretty much the same kind of set stuff with relations that you would do with ordinary sets. Okay? So the union operation basically takes a union of two relations in R1 or R2. The notation for the union operation is R1 U R2. Important caveat here, R1 and R2 need to have the same schema in order for you to be able to do this operation. If they don't have the same schema, it is meaningless to actually do a union. It is not allowed. Okay, so they have to have the same schema. And the output R1 union R2 has the same schema as R1 or R2. Right? So for instance, if I have a relation active employees with attribute SSN and name, and a retired employees relation with attribute SSN and name, and notice once again the schema of these two relations is the same, which is the only way I can actually do a union. I can find the set of all employees that are either active or retired, so the set of all employees, right, by doing a union between active and retired. Okay, so then you have difference. These are all tuples in R1 but not in R2. Once again, R1 and R2 need to have the same schema like in union, and the difference has the minus sign just like in set difference, and the output R1 minus R2 has the same schema as R1 or R2. So an example here is all employees minus retired employees would for instance give me the set of active employees. Right? Again, for this to make sense, all employees and retired employees need to have the same schema. Okay, so this is standard stuff. Let's talk about more interesting operations. So here's an interesting operation. This is a selection operation. The selection operation returns all tuples in a relation that satisfy a condition. The way to represent a selection operation is using a sigma with a condition as a subscript, and then you have the relation R inside in parentheses. C is a condition which uses equals, less than, greater than, and, or, not. Right? So these are various things that you can use within this condition in the selection clause. This condition is also known as a predicate. Okay, so this is a predicate that you are using to select the tuples in your relation. When you apply a selection, the output schema of the new relation that comes as output is the same as the input schema, because all you're doing is selecting some of the rows. So for instance, if you have a query which is find all employees with salary greater than 40,000, I would have a query that looks like this. So I have the relation employee here within parentheses, a sigma operation here, and salary is greater than 40,000 as my condition. Yes?
So what if like none of these satisfy that?
You'll get an empty relation. You'll get a relation with the same schema as the employee relation, but that relation won't have anything. Yeah. Any other questions? Okay. So here's an example of the selection query on a relation. So let's say I have these three employees, John, Tony, and Alice, and I want to find all the employees with salary greater than 40,000. I'll use the same query that I issued earlier, and essentially you can think of a selection condition as going through each tuple one at a time and then deciding whether it matches that condition. So you say, hey, salary is greater than 40,000, this doesn't satisfy. Salary is greater than 40,000, this doesn't satisfy. Only the Alice tuple satisfies, therefore the relation that is output only contains the Alice tuple. Okay? And you can also have more complex conditions. Here I want to find the employee with salary greater than 30,000 and department ID is equal to 2. In this case, again, the Alice tuple is the only tuple that gets selected. Right, so both of these tuples get discarded because you don't satisfy ID is equal to 2. and Alice gets selected because department ID is 2 and salary is greater than 30,000, right? So you have this as the output of the selection query. How do you use not in a condition? So you can do not salary is equal to 30,000, which basically says salary is not equal to 30,000, right? So you can treat these as you can think of them as Boolean operations, and then you can operate on them as Boolean operations. Any other questions? Okay, so we talked about discarding these rows, right? The next question is, can you discard some columns? And for that, we have the projection operation. So the projection operation, like the selection operation, is a unary operation. It applies on one relation, and it returns a certain subset of the columns of that relation. Okay, so one important thing to note about the projection operation is that it will eliminate duplicate tuples, because, like I said earlier, a relation is a set of tuples. It's not a list of tuples or a bag of tuples. At least from the relational model standpoint, it is a set of tuples. So one issue with a projection operation is that it can lead to duplicate tuples. And so at the end of the I don't know if I said projection or selection, so let me repeat that. So one issue with the projection operation is that it may lead to duplicate tuples. In order to avoid that, the projection operation at the end will try to collapse down duplicate tuples to have only one copy of each tuple. Okay? So, I don't know why this sometimes happens. So the pi operation is the projection operation. The notation once again is pi. And the way I select a set of columns that I care about, let's say I want to select A1 through AN, is basically to list them as subscript of pi. And so if the input schema is B1 through BM, then I need that A1 through AN, which is the subset of B1 through BM, so is actually a subset, right? So I need the output schema to be a subset of the input schema, because what I'm doing with the projection operation is to discard certain columns. So potentially I might discard 1 or 0 or all of the columns, right? Maybe not all of the columns, maybe all but one of the columns, right? If you're discarding all of the columns, it's probably meaningless. So so you want to use the projection operation to discard one or more columns, and therefore the columns that you are selecting need to be a subset of the columns that are present in the original relation, right? So if you say, hey, pi A1 through AN of blah, this would select attributes A1 through AN. Only A1 through AN will be present in the output. Okay, so the output schema is A1 through AN. So here, if I wanted to take a relation with employee, SSN, name, department, salary, and I wanted only to take the SSN and name out of this relation, I don't care about department or salary, I would do pi subscript SSN comma name of employee. Right? Okay, so here's an example of using the projection operation. Once again, my symbols are missing. So if I had this as my relation and I wanted to select SSN and name from this relation, I would essentially get rid of these two columns and then collapse duplicate tuples. Right? So in this case, there are no duplicate tuples in SSN and name, so you have SSN and name returned as output. On the other hand, let's say I wanted to select only department ID, right? If I wanted to select only department ID, so I wanted to project department ID of employee, so department ID is the only attribute that I cared about, then how would I do this? Yeah.
You only get 1 and 2.
You'll only get 1 and 2, right? So one way to think about that is to throw away all of these other attributes. Now you're just left with this attribute, and then you want to collapse it down so that you have one copy of each of them. So you would basically have your output relation be department ID with 1 and 2. Okay, so that's going to be your output relation. Any questions? All right. Okay, so comparing selection and projection. So how are they different? Well, they are both sort of single table operations. On the other hand, they are different because one of them is removing rows, the other one is removing columns. Both of these are essential because they are both types of operations are needed. Often you may want to focus your attention on a certain set of columns that you care about, and you may want to focus your attention on a certain set of rows that you care about, right? So both of these are essential to any database query language, right? So, and therefore they are part of the foundation of relational algebra. Then the last basic operation is the Cartesian product operation. This should be familiar if you know Cartesian product from other contexts. Cartesian product basically tries to associate every tuple in one relation with every tuple in the other relation. The way to represent that is using an X. So R1 X R2 is basically saying take the Cartesian product of R1 and R2. The input schemas, let's say the input schemas for R are A1 through AN, for R2 is B1 through BM. For now, let's assume that the intersection of A1 through AN and B1 through BM is the null set, so is the empty set for now, okay? So how do I represent the output of this Cartesian product? This Cartesian product output schema would basically be A1 through AN followed by B1 through BM, so it's just a list of all the attributes. As it turns out, the Cartesian product is actually very rare in practice. You don't really use it that much. So this particular basic operation is not used as much as the other basic operations, but the other operations that are derived from Cartesian product, which we will talk about later, are actually used very, very frequently. So the join in particular, the theta join and the natural join are used very, very frequently compared to the Cartesian product. So the Cartesian product still offers us a useful building block in composing those operations. So here's an example of the Cartesian product. So let's say you have name and SN in one relation, and employee, SN, and department or dependent name in the other relation, and you wanted to do a Cartesian product of the two relations. Its output schema is a list of all the attributes, so all of these 4 attributes, and basically you associate each one with each one in relation 1 with each one in relation 2, right? So you have 2 tuples here, 2 tuples here, so you would have 4 tuples as part of the output. Yes?
So can you have like duplicate tuple, like duplicate tuples in one like let's say employee, so you would have another like John and then like the same data, or is it like not allowed?
Okay, so in the vanilla relational model, relations can never contain duplicate tuples. So relations are a set of tuples, therefore they contain only one copy of each tuple. And because this is an exercise for you guys, given that the relations obey this property, try to prove for yourself that operating on the relations in this way, so Cartesian product, selection, projection, all preserve the same property. Projection is the only one that you actually need to worry about because it may introduce duplicates, but projection explicitly tries to eliminate duplicates at the end of it. The other operations, in this Cartesian product case, if the relations are unique in relation 1, if the tuples are unique in relation 1, tuples are unique in relation 2, when you do a join, you're going to get unique tuples as the output. Okay, so that's the reason why this still doesn't violate the property. Yep.
Sorry, I still have a question about projection.
Yep.
So what if so we did the example, what if we try to put projection, subscript, department ID and name, which do you choose? The second one, or the first one?
Okay. So if your projection was department ID, comma, name, then you are going to, so the first thing to do is to eliminate all of the other attributes, okay? Now, there are no duplicate tuples.
Right, so it would be John and Alice.
You know, you would be returning all three of them,
Oh, right.
right? Because these two are not duplicate tuples. They have a common attribute, department ID, but they're not duplicate tuples, right? Yeah. Any other questions? So for tuples to be duplicate, they have to have the same value for all attributes.
So if it was Tony and Tony, which Tony would you use?
Yeah, so if you had Tony and Tony, you could use either one. It doesn't matter, right? Any other questions? Okay. All right, so one note about the Cartesian product is we had this condition where the attribute sets had to be disjoint, but that's actually not necessary in the Cartesian product. The convention that we use is if an attribute AI is the same as a different attribute Bj, then you would basically rename them as R1.ai and R2.ai. Okay, so if it is the same attribute name, you would just preface them with the relation ID. Okay, so that's just a convention that we follow in order to get rid of the case where the intersection is not null. Okay, so I don't know why this symbol shows up sometimes but not others. Anyway, so the last sort of basic operation doesn't count as a basic operation, but it's useful to change the schema, is a renaming operation. The renaming operation does not change the relational instance at all. Okay, so it doesn't change the relational instance. The only thing that it changes is the schema. It doesn't change the data, it changes the schema. So if your input is R with attributes A1 through AN, and you wanted to rename it to S is the relation name and attributes B1 through Bn, you can basically use the renaming formula, which has a notation row, has a subscript with the new relation name and the new set of attributes with in parentheses R. So notice that these two have to have the same number of attributes, right? If you don't have the same number of attributes, then it's not entirely clear how to sub-select the list of attributes in the new relation, right? So they have to have the same set of attributes. So if I wanted to, for instance, rename employee with attributes name and SSN into renamed employee with last name and SOC sec number, maybe, I would do it in this way. Okay? Yes?
If you don't want to change like name, for example, then it would just be rename employee's name and then SSN.
Sure. Yeah, if you didn't want to change the name, you just wanted to keep it as name, you can still have it renamed employee name, comma, SOC sec number. Yeah. Any other questions? Okay. All right, so let me see if how much I can cover in the next couple of minutes. Maybe I'll cover this example, it's pretty easy. So if you have an employee with name and SSN as your two attributes, and your new relation is called renamed employee with last name and SOC number, your new relation would have those two as your attributes. Okay, so let's quickly talk about the derived set operations. Those are very easy, so I'll cover them quickly. So we talked about union and difference. There are other set operations like intersection. Intersection basically have the notation is inverse cap or whatever, inverse U, and the constraint is that R1 and R2 have to have the same schema, just like the other set operations. So I might want to do an intersection between unionized employees and retired employees to find the employees who are both unionized and retired, right? And the way to derive intersection using the other operators is basically R1 minus R2 gives us the intersection operator. So it's a derived operator. Okay, so maybe I'll stop here and I'll cover the rest next week. Okay, any questions about this stuff? So I know this is a little tedious, but once we get past the syntax, once we get to creating queries, it gets more interesting. Okay, so bear with me until then.